Okay, so now we have Wenjia, and she will talk about a gradual probabilistic lambda calculus.
Hello everyone, I'm Wenjia. I'm a PhD student from the University of Hong Kong under the supervision of Bruno Oliveira. Today I will talk about the work with Matías and Federico from University of Chile. The paper named Gradual Probabilistic Lambda Calculus. Suppose you have a simple application with authentication, and you have a user that Suppose you have a simple application with authentication. You have a user that connects to a login web application for a company, and then to authenticate, you prefer to ask if the user exists in the database of the company or not. So you consume a web service. And the web service is going to respond either this user exists or not exist. But this is not the only answer, because you could say, okay, if the API does not have connection to the database, then it's going to give you an error. We can zoom over the login module, and then you have two different modes, like development mode and or production mode. If you try to log in like Bob with some password, then the code related to that part of is this one. Before returning the login is correct or not, you first ask if the user is active or not. And the user is active is going to consume an external web service if you are in production mode. But if you are in development mode, then you don't want to consume the external web service. Maybe you just want to return true or false with a local code. Empirically, you can check that the web service has a 90% uptime. And your boss tells you that you have to have 95% uptime. If he asks that and you don't do anything, you just run with this program and you just put this in production mode, you are going to fail to detect the impossibility to comply with the requirement because you don't do anything. So to model this specification, you can use probabilistic choice N(O) plus N. This means that this expression behaves like M with probability P and with like N with probability 1 minus P. And you also have this probabilistic type, meaning that the type T subscribe I occurs with probability P subscribe I. If you use the combination of these two things, probabilistic choice and probabilistic type, you can type the external code with this type that is going to return a Boolean with 90% probability and an error with 10% probability, because this is the empirical information that you have. Maybe your local code can be type checked with as such, like it's going to succeed with 95% probability and an error with 5% probability. You can type check the whole program like this. the external code has a 90% probability of success. Local code has a 95% probability of success. And if you mark its user active as a function that has a 95% probability of success, the external code is going to be yield type because the external code has 90% probability of success and you are expecting a 95% of success. So it's very conservative. To address this, you have gradual typing, where you can use unknown to represent any type because any type which causes error. So instead of fixing its user active with a 90% probability, you can set it as unknown as while you are in developing mode. You can develop freely without worrying about failing. And if you are in production mode, you are going to fail at runtime. Yeah, so this is what happens. If production mode is true, then it's going to fail at runtime because 90% is not equal to 95%. And if production mode is false, then it runs successfully. This is done by consistency relation. We can detect errors because consistency is not transitive. So here you have an example says that a 90% Boolean is consistent with unknown, and unknown is consistent with 95% Boolean, but transitive does not hold. So what we do is that we check at runtime if those type annotation is respected at runtime. If we add more annotations, if we increase the precision of the program, we are going to make the term yield type. Because now we are going to statically detect that we are not satisfying the 95% requirement that we have in the login function. So besides that, we are able to encode imprecision probabilities. For instance, what if we want to specify that external code has an uptime of at least 95%? We do this by defining Boolean as 95% probability. And then also, you can have a Boolean with unknown probability and an arrow with unknown probability. There you have imprecision in the probabilities. And these unknown probability are subject to, of course, the probability has to sum up to 1. Another thing that you can do with this system is that you can synthesize probabilities. For instance, suppose you have a load balancer. You have many login attempts. So you want to balance the load of this access. This load balancer is going to sometimes derive you to a cheap server, and sometimes it's going to derive you to an expensive server. Besides, you know that the cheap server has a 90% uptime, and of course, it's very cheap. On the other hand, the expensive server is a very good server, and it has a 98% of uptime, but it's very expensive. If you want to ensure or guarantee at least 95% uptime, how should we distribute the request? So to know this answer, you could model this problem using gradual choice probabilistic. In this case, you can model the cheap server as a function that returns something with 90% probability, and the expensive server returns something with 98% probability. The external code is going to use a probabilistic choice, and the probability of the choice is going to be unknown. This is going to be type check, and at runtime, you can use symbolic variable to represent unknown probability. So you can run the program to know what are the restrictions for this symbolic variable in order to satisfy the requirement. At runtime, the main contribution is that we detect that the coupling as a key center pieces, and plausibility is composed of the use of coupling, the use of constraint, and the satisfiability of this constraint. For instance, if you have this consistency relation between unknown with probability unknown, and real with half probability and Boolean with half, then this unknown with probability is going to represent like this, and the other hand is going to represent like this. So this will induce this lemma, this formula. So the coupling is going to induce the lemma to know if this consistency relation holds. We ask a SMT server, for instance, if this is satisfiable. So this could be more complex, and the answer will not always be 1. So we just list this example. And these are the constraints, and you can see the answer is not is a range, not just one solution. Going back the example, if you analyze the possible answer for the constraints, it's going to give you that the probability has to be less or equal than 37.5%. If you choose any probability less than that, you can guarantee that the probability is going to be at least 95% to satisfy the requirement. And what's more, in the paper, we have a formalization about this language. We define a source and a target language. We show how to leave relation on gradual type to relation on distribution types using couplings. We also show operational semantics, define over distribution of values, and we show some properties such as type safety and the gradual guarantee. And the gradual guarantee is the most complicated property to establish. If you have a function foo, which reduces to true with half probability, and if you take a less precise version of the program, it should always also return a value according to the gradual guarantee. But in this case, this could reduce to the same probability, but to an error. So this seems that the dynamic gradual guarantee doesn't hold. But actually, what you have to do is to compare the value distribution of these two executions. So the first value execution is going to give you true and error with half probability each. And we say that is more precise than the distribution of true, unknown, and error with half probability each. So the dynamic gradual guarantee holds if we analyze the whole value distribution, not just for like the single execution. And we can, and to know more about the coupling, which we also use for the dynamic gradual guarantee, we can have a look for this more complex example, which I have mentioned, but I haven't go into the detail. So you can have many answers. For instance, here you have, for consistency, you have two types. So a real with 1/2 and an unknown with 1/2. On the right, you have unknown with 1/3, a real with 2/3. You have many possibilities. You can connect the first with the second one, the first with the first one, and so on. If you write the set of constraints, it's going to something like this. The interesting thing is that you don't have, you can calculate this for, you can calculate for this symbolic variable, and then you can like in program, like in synthesize probability, you can have a range where you can choose for like to satisfy some requirement. Okay, and thank you.
Questions?
Hi, thank you for the talk. I have just one quick question. Do you support recursive definitions in your language?
Sorry?
Sorry, do you support recursive definitions in your language? Like
Definition?
Recursive definitions.
Recursive definition?
Yeah.
What kind of recursive?
Like, for example, a factorial function with a non-deterministic choice, or just a loop, an infinite loop where you choose that?
No, we don't have
Okay.
Infinite loop.
Okay, thanks.
Yes, thanks for the talk. I'm just trying to have an idea of the type system. So you can have those distribution types. It seems like if you erase the probability, is it like union types to some extent? Because you can have a set of different values. Is that how we should think about those distribution types?
So you mean for the distribution type, it's like a union?
Yeah, is it a good intuition or?
Yeah, I think you can because it's because it's some like you have a set and this set you have many types and this type has their probability. So I maybe but for union you don't have a constraint that the probability has to sum up to 1. So I think you cannot.
Yeah, right, like quantitative unions,
Yes.
so to speak. And then I guess you can only use ground types, but not higher order types, for example. Like,
Ground type?
Function types. I guess you don't have function types.
Oh, we have function type.
Within the unions, like you can have a distribution
mean-
types of function types?
You mean in union you can have function?
I mean, in your distribution types, can you have higher order types, function types inside?
Oh yes, we have function type
Okay.
inside the distribution type.
Okay, thanks.
Thank you.
Sorry, I had a question about your dynamic gradual guarantee. The example you showed had the distribution, the value itself in the distribution was becoming more precise. It was going from dynamic to precise value. But can you also increase the probability of an error when you add type precision to a term?
At the precision in error.
Yeah, so when I change the precision of the term, couldn't I increase the probability that there's an error as well?
I think because they are the symbolic variable. So so for the probability for the exact number is calculated during at runtime for the probabilistic. For the probability.
Okay, so I couldn't go from because it could be if expression, then flip a coin, and then I could make that expression more precise and cause there to be a type error, and so the precise one would have a distribution heads and tails is 50-50, and then the precise version would have 100% chance of type error at runtime, right?
No,
I mean, maybe it's too
Maybe you
technical.
can take it offline.
Yeah.
I think maybe not because because it's just check the dynamic gradual guarantee is checked by like in the coupling, and you when you check the coupling, if you have 100% of error, then you cannot satisfy the coupling.
Okay.
Yeah.
But I want to talk more about
Okay.
that.
Thank you.
All right, let's thank the speaker one more time.